Well, hello and welcome. In this video, I'll be covering section 1.4, which is over functions. And my goal for you by the end of the video is to be able to decide whether relations between two variables are functions, to be able to find the domains and ranges of functions, to be able to use function notation and evaluate functions, to be able to combine functions and create other functions, and to be able to find inverse functions algebraically. So let's start with the definition for what a function is. Hopefully this is all review, but it can never hurt to cover it a second time. So first, we need to, define what a relation is. So a relation between two variables is when one of the values of the, relation depends upon the value of the other variable. So if you have a column of x's that pair with y's, that would be something that we would call a relation. That means a relation will have two variables, which then we can call one independent, so think like what I would plug in, and the other one be dependent, which would be like what the result would come out as, or the output. In order for a relation to be able to be specifically called a function, it has to have a relation between those two variables where each independent has exactly one dependent. So another way to think of that is one values getting plugged in and then a single value is coming out. Now with functions, remember, it's okay for one value to go in, turn into a number, a different value to go in, but then turn into the same number because again it was two different inputs gave us a single output each time. Now the concept of domain and range with functions, the domain you can think of as it's just all of the set, or the set of all of the defined independent variables, or your input values, so all of the things that are allowed to be plugged in, and then the range is always the set of your dependent variable, or all of the things that are coming out. So let's try a couple of examples where we're just going to establish whether this relation that is here, so notice every one of these has two variables, so they're all relations, but determine which ones specifically define a function of x, or as a function of x. So in this case, that's telling us that x is our input, then y must be the output. Or you can think of it as x is your independent variable, y is your dependent variable. So what we really want to do with each of these to just determine whether this defines y as a function of x is to just get y all by itself. So do whatever math I need to actually isolate the y. So with this first one, I could subtract x over to the other side and get negative x plus 3 is equal to that negative y, but then divide by negative 1 or multiply by negative 1, however you like to see that, and get y is equivalent to x minus 3. In this case, every single x that I would plug into should give me a unique y, so this one would be a yes. This is a relation that I could call a function because I was able to isolate y, and it only would give me a single y for every x that I would plug in. The next example, if I work through the same approach, I would just move the x squared over to the other side first. So I'd end up with y squared equaling, and I could write this as negative x squared plus 9, but with this one I'm going to go ahead and just write it as 9 minus x squared to protect that negative a little bit. Because I am thinking ahead, the next step is going to be take a square root. Having a negative first inside of a square root is kind of weird to see, but this one, because we took a square root, I'd end up with that plus or minus symbol. So now it's for each x that I plug in, I actually get a positive and a negative result. I'm not supposed to have that happen, so this one would be not a function. It's still called a relation, I just cannot call it specifically a function because of that symbol right there. I get two different answers every time I plug in the same x value. Let's try the next one. Similar start, move everything that's not a y over to the other side. So I'd end up with 2y being equivalent to 12 minus a 4x squared. Again, I could have wrote that as negative 4x squared plus 12, but it won't really change a whole lot of what's going to happen here in the next step. Divide everything by 2, I'd end up with a 6 minus 2x squared. I didn't introduce any sort of plus or minus symbol, so that means for each individual x I plug in, I get one single y that would come out. So this one is another yes, like the first example. And the last one, do the same steps, move the non-y terms over to the other side. And I have to cancel that power with the square root. Since I introduced a square root, I get a plus or minus. And that then would tell us, since there's a plus or minus symbol, every x that I plug in, I get a positive and I get a negative. That's two outputs for the same input. Oop, I don't know why I'm writing yes. That is a no. Don't talk and write at the same time, right there. So, similar, B and D in this case, notice they both ended up having a square root get involved, which then turned into a plus or minus symbol that we needed to, I guess, have in front of it. So that gives me two possible answers for every input, hence why these both were no's. The other ones, even though I had a power on the x, I never had to cancel the power because y had a power of 1 on it. So this one and the first one, A, ended up having only one output for every input. So those would be functions. Now moving on to more of the graphical representation of functions. Remember with this, again, this hopefully is review for you guys, but we have this concept called a vertical line test that we can use to actually just visually tell whether something is a function or not. One thing that I don't know if you've been as careful with, because more times than not we've just had x be our input, y be our output, so our normal coordinate plane has been able to, I guess, apply this vertical line test, but it is important to note that the horizontal axis does need to be representing your independent or the input variable in order for the vertical line test really to be something we can apply. Again, more times than not, the horizontal axis is already going to be the independent variable, so you don't have to look at it that close, but it is always important to note. The reason why the vertical line test works is if you have, say, a graph that kind of twisted backwards and we had a vertical line that crosses through it. Let's say our origin was like right here and our graph was up to the side, and I have this vertical line at whatever this value is, like A. That means when I plug A into the function, I get three different answers. I get one answer here, I get a second answer here, and I'd get a third answer here. And again, in order to be a function, by definition, it's only supposed to allow us to have one output for each input. That then is showing that there's three outputs, hence why we would say that's not a function. Now another test we can do was called the horizontal line test, down here at the bottom. And what a horizontal line test really told us was whether a function was one-to-one. So a vertical line will tell us whether we have a function. Once we've established we have a function, in order to tell whether something is one-to-one, I basically need to just verify that every y is only going to pair with exactly one x. So it's kind of each x gives us a unique y, and every y has a unique x, in order for it to be, again, considered one-to-one. So if you had a graph like a, say, parabola, a horizontal line going through that, notice that means that there are two different x values, right? One here and one here, that have the exact same y values, so that would be something that's not one-to-one. Now if I had something that was constantly going up the page like this one, and say our origin was maybe like right there, now every horizontal line I draw only touches the graph one time, so that means that there's one x that pairs with exactly one y, hence me being able to call that one-to-one. Now by this point, if you've made it to this class, this idea of function notation should not be anything that's brand new for any of you, but just to review it, function notation is generally something that we use anytime we isolate the dependent variable. So remember, this idea of function notation was like everywhere I see a y, I technically could just replace that with a function notation such as f of x, where this letter in front, so in this case the f, would really be like, that's my name of the function, that's just my identifier, and then the what's in the parenthesis tells us that's what our independent variable is. In other words, the thing that I would be plugging in. So again, generally, in order to be able to make something into function notation, I have to isolate the dependent variable. More times than not, it's been y in your guys' past, and then I can replace it with the name of a function. Could be f, g, h. Those are like our three most common ones. But then we have on the inside of the parenthesis, it's what our independent variable is, or what variable I should expect to see. So as you can see with the example that's here in the middle, it's saying that x is the input, f is the name, and that means the only variable I should see is x is inside of that function. If there was a y over here, then the function notation would not be accurate. So to read that aloud, remember the f parenthesis x idea there, what we call that or say out loud is just f of x. It's letting us know or indicating what variable I actually am going to be plugging in for. So when it comes to evaluating, let's say at a specific number like f of 3, if I use the example from above, I would just plug 3 in everywhere x is, so it'd be f of 3 is equal to 1 over 2. I see x, so I'll put the number 3, and then I have another plus 3 still that is a part of the function. So at this point I should be able to, once I've established a number has gone in, I should be able to simplify. On the bottom I'd have 2 times 3, which is 6, plus 3 more, which is 9. And if I could reduce that fraction I would, but 1/9 is as good as it gets. So what that would mean in a table or as an ordered pair is the point 3 comma 1/9 must be a solution point or a point on the graph of that specific function. So let's work through a few examples of this evaluating a function at a value or expression. So this first one is going to be as simple as possible, more than likely. It tells us that I need to be plugging 2 into the function. So everywhere I see x, which there's 2 of them, I'm going to replace with 2, so it would become 2 quantity squared plus 2 times 2, then minus a 5. So at this point I would just simplify each of those values. So 2 squared, that would turn into 4, plus 2 times 2, which is 4, and then take away 5. So I've got 8 take away 5 really, which would be 3. If I look at the second example, now I'm actually plugging an entire expression into that place, or the place where x is in the function. So this one we'll start with, I'll put x minus 1 quantity squared plus 2 times x minus 1, then minus 5. And good practice is, anytime you do a substitution, especially when it's an expression like this, is to throw parentheses around it like I did, to remind yourself that you may need to expand out some powers or maybe distribute things through, which are going to be the next 2 steps. So with this one, if I expand out the x minus 1 squared, that should give me x squared minus a 2x plus a 1. Then distribute the 2 through, that would give me a plus 2x and a minus 2, and then I still have the minus 5 at the very end. So now it turns into a combining like terms problem. If I combine my like terms, I've got x squared, there's no other x squared, so that's only one I have of those. I have a negative 2x and a positive 2x, they actually will reduce down to a 0. And then 1 take away 2 would be negative 1, take away 5 more, so negative 6. So this particular function, when I evaluate it at x minus 1, simplifies down to this x squared minus 6. Now onto probably the most complex one in this example, or for this slide. This is what's called the difference quotient. Should have been something that was presented back in pre-calculus at some point in time, but it's going to pop up a little bit more consistently here as we move forward. But this concept of the difference quotient is we're plugging in x plus delta x, and so again the triangle x, we say that as delta x to stand for like a change in x. So I've got this expression x plus delta x that's getting plugged into the f function, so where those two x values are in that, I'm going to replace it with the x plus delta x. So I've got x plus delta x quantity squared first, then I've got plus 2 times the x plus delta x, then minus 5, and all of that is being plugged in this spot. So since I'm doing kind of a substitution type idea into this big fraction, throw some parentheses around it just to show I've done that substitution. I follow that with a minus sign, and now it's going to be plug in f of x, which in this case is just the original function x squared plus 2x minus 5. All of that still is being divided by the delta x that's on the bottom, so that has not been able to simplify. Now I just expand out all of my parentheses as best as I can. So it looks like the first one, I'll just need to square that binomial. So that would give me x squared. I'd have an x times a delta x with another x times delta x. So that would be a total of 2x times delta x. And then a delta x times itself, so that would be delta x squared. Distribute the 2 through the next parenthesis. That gives me 2x plus 2 delta x, and then still the minus 5. The second part, I just have this minus sign to distribute through, so that would be a negative x squared, a negative 2x, and now a double negative on that 5, so a plus 5, and then still again all over the delta x. So now moving on to the next thing, which would be combine as many things as I can on top. If I look at some of the things I have a positive x squared and a negative x squared, so those two actually should reduce down to a 0. I do have a positive 2x and a negative 2x that will cancel out, and I have a negative 5 and a positive 5 that cancel out. And so now I'll just collect my terms. So it looks like I've got a 2x delta x. I have a plus delta x squared right here, and then I have a plus 2 delta x, and still all over the delta x. But as you can see on top, they all have a delta x, so I could just factor that out. So that would turn into delta x in front, leaving 2x plus delta x, then plus 2. And why I would want to factor that out is because now at this point I have delta x divided by delta x that would cancel, leaving me the final expression here of 2x plus delta x plus 2. So super ugly work going through that one, but notice the process of being able to plug in and then just try simplifying. If you slow it down and make it small parts, hopefully that makes it easier for you to accomplish. Now that we've talked about the definition of functions and how domain and range are found, again, just a reminder, the domain is what you can plug in, the range is what you can get out, and then actually the evaluating of functions. Let's go ahead and talk about how we can combine functions. So combining functions, as you can see, the left side of each of these is like the shorthand, so f plus g of x would be how I say that statement right there. F minus g of x, f times g of x, and f divided by g of x. Notice what we're able to do is actually split that up and just say, okay, well technically x is being plugged into each equation, and then I add those two results together. So f plus g of x is again the shorthand of saying it's really f of x plus g of x. It really is only just allowing you to kind of only have to write the x value one time. Now off to the side here, I'll go ahead and work through how these examples really work, but the first two, f plus g of x and f minus g of x, those really are going to just turn into combining like terms type problems. It's just the f minus g of x, you'll have to be a little bit mindful of maybe throwing parentheses around whatever the g function is to remind yourself that you may have to distribute through that negative sign multiple times, however many terms there might be. So with this, I'm using the f of x equaling 2x plus 1, as you can see on the top right, and g of x being x squared plus 1. If I wanted to do f of x plus g of x, that really would be 2x plus 1, that I would then add with x squared plus 1. And again, good practice is to kind of put parentheses around that just to remind yourself if there's something outside that keep those to go ahead and distribute through. But in this case, there's just ones in the front of each of these, so I really don't need to distribute out. The parentheses can be just dropped. So it looks like I only have one x squared term. I've only got one x term. And then I do have a pair of ones that I could then add together and actually turn into 2. So the f of x plus g of x would turn into this new quadratic x squared plus 2x plus 2. If I did f minus g of x, that would be 2x plus 1. Again, if there was a number in front, I would go ahead and make sure that I have parentheses to remind me to distribute, but I don't have to distribute on that parenthesis. This one, though, I do have the minus, so by throwing parentheses around it, this one, it would hopefully catch my attention that, oh yes, I do need to actually distribute that negative through. So if I did that, I now, as you can see, would have a negative x squared. I'd still have a positive 2x, and now I have a positive 1 and a negative 1 that actually would cancel out, or reduced to 0, so that actually would be my simplified subtraction problem of f minus g. Now f times g of x, that usually is going to turn into like a distribute or FOIL or Punnett square type idea, whichever method you prefer. In this case I'll be able to do it like a FOIL because it is a binomial times a binomial. But I just rewrite the two functions, f and g, throw a multiplication symbol in between. Having two parentheses next to each other implies that. And now just distribute everything through. So if I did that and collected my terms, I have 2x times a x squared, that would be 2x cubed. At 2x times a 1, that would be a 2x. Move on to the second term, I've got 1 times x squared, that would be x squared. And then a 1 times a 1, which would be a 1. And I personally have the OCD nature of I want to write this in a descending order, not a mixed order, so I would go ahead and just kind of rewrite those middle two terms in a different order so my power decreases as I go. Do you have to do that? No, but that's just, again, that's my personal preference. I always like having some form of order to what's going on. Now the last one, f divided by g of x, usually this is the one that actually has the least amount of work, because you essentially just make a fraction, and then at this point you would look to see if you could factor either part and maybe cancel some stuff out, but this one cannot really reduce in any way, shape, or form. So this actually is the result just by writing f on top and g on the bottom, and then again just looking for any way to simplify it. This one can't be simplified, so that would be my final answer. So another way that we can combine functions is to form these things that you might recall as composition functions. So composition, the indicator that tells me I'm composing, is this open O. It's not a multiply, that's a compose, where it's going to be the g function is being composed into the f function. So you kind of work from back to front as opposed to front to back. So with this one, that symbol again, that O, is telling us that we are plugging a function into another, and it's really saying that the g function is going into the f function. So you can denote it this way if that helps. Anytime you see that, you can automatically convert it to where the f function is out front, and then inside of that function it has the g of x function. And what's important to note with this one is the domain of f of g of x. The order technically is going, x would go into g to create g of x, so you'd have to make sure that everything is allowed, all the x's that are allowed to go into g would be the first part of your domain, and then the results that come out of that plugging in need to make sure that they satisfy whatever restrictions maybe the f function has. So as this says, it's a set of all the x's that are in the domain of g, such that the results from that are in the domain of f. And we'll do a domain type problem here coming up soon. With this one, I just want to kind of show the two compositions, f of g of x as well as g of f of x, and just kind of show that this idea of composition is not a commutative idea. In other words, the order, when you switch it, is more than likely going to give you a different result. So let's go ahead and try this first one, f of g of x. So I'm just rewriting it using the notation without the operator or the O, and then I go ahead and say, okay, well the g of x function, which is x squared plus 1, is going to go into the f function everywhere x is, so that would be 2, replace the x with g of x, and then finish up whatever the f function was. This one's relatively straightforward. All I'd have to do is distribute that 2 through, so I'd have 2x squared, then I'd have plus 2, but then plus 1 more, so a total of plus 3. So that would be my composition f of g. If I move on to the second example here, where I'm going to do g of f of x, now it's the f function that's being plugged into the g function. So I have an x that I need to replace in the g function. So it starts right out with it. That's where f of x is going to go. Quantity is being squared, and then I still have the plus 1 on the outside. So if I distribute this parenthesis out, again squaring a binomial, that's going to turn into 4x squared. I'd have a 2x in the middle with another 2x in the middle, which would combine to give me 4x, and then a 1 times 1 for my last term, so 1, and then still plus the extra 1 from the end. So it looks like there's only one like term with this one, of the 1 plus 1, which I can then simplify and call 2. And if you really wanted to, with this one, we could have factored a 2 out, but it really wouldn't help us in any way, shape, or form, so why do the extra step? That should be good enough. So as I mentioned before, these types of problems, the compositions, can also have this concept domain get involved that we would need to maybe potentially answer. So anytime you have a domain question with one of these compositions, my recommendation to start is to actually figure out what's the domain of each of the individual functions, and then more than likely we're going to have some form of combination of those two when it comes to the compositions. So this first one, if we think in terms of, okay, it's got a square root, so there are some restrictions, it just can't be negative on the inside. Well, it would equal 0 at -4, and if I chose numbers that were greater than -4, such as like 0, the inside would be positive, so it's going to be everything from -4 to infinity, but include -4 because square root of 0 is still acceptable. With the second one here, it's a rational function, so this is one of those where I just need to make sure that the denominator is not equal to 0. So at this one, the number that would make that equal 0 is 2. So I would just need to double check and say that my domain is everything except for x being 2. So if we now move on to the compositions, the f of g of x, if I go through what are some of the things that I know, well, with this one, just how it's built, I know that the x is going to go into g first. So if I think in terms of, okay, so is that meaning everything can be plugged in this scenario? No. Thus far I've established I for sure am going to have to get rid of 2. However, I'm not done. I need to think of the results that come out of the g function, make sure that they're still acceptable in the f function. So with that, I would take whatever the g function is and just make it greater than or equal to whatever the smallest value is I can be for that radical, which in this case, the smallest value I can equal is -4, because I want to be either -4 or above, because I'm going towards infinity with that one. So to solve these types of inequalities, I have to get 0 on one side first, so I'd add 4 to both sides. That would give me 1 over x minus 2, then plus the extra 4 that's separate, being greater than or equal to 0. And so now at this point I would need to get a common denominator, so I'd have to multiply by x minus 2 on top and on bottom. And if I distribute that through the numerator, I would have 4x, then I'd have 4 times -2, which is -8, but then plus 1, so -7. And then all over the denominator that I made both fractions have, which was x minus 2, and now it's greater than or equal to 0. So now I can just figure out my critical numbers. What makes the top equal 0? Well, that would be add 7, divide by 4, so 7/4 is going to be a number that's of use, and then whatever number makes the bottom 0, well, that would be 2, which we already kind of established earlier. And so I would just throw those on the number line. In this case, 7/4 is a little bit less than 2, because 2 really is like 8/4, so 7/4 would come first, and 2 would come after that. Or you can also think of 7/4 really as like 1 3/4, so it's like 1.75. That might help when it comes to our testing of the intervals, because they're so close to each other. But if I choose a number that's less than it, less than 7/4, so something that's on this first interval right here, a number that was there that's probably easiest to plug in would be like 0. If I plug 0 in for the two x's that I have in my fraction over here, I'd have 0 take away 7, which is negative. I'd have 0 take away 2, which is negative. But two negatives when you divide actually give us a positive result. So that part, that interval from -infinity until 7/4 is going to be able to be a part of my domain. -infinity until positive 7/4. And it looks like I should be able to include 7/4 because it wasn't equal to 2. So let's move on to the next one. If that's 1.75 right here at 7/4, and that's 2, then maybe a number like 1.8 we could maybe test with it. So if I multiply that maybe with a calculator, I'd have 4 times 1.8. That's for sure going to come back positive, and then take away 7 from that result. That goes out as positive 0.2 according to my calculator. On the bottom though, if I did 1.8 subtract 2, that would come back negative. A positive divided by a negative should come back negative, so that interval is not going to be a part of my solution or my domain. And then the last one, test a number that's greater than 2, so a number like 100 would be sufficient enough. If I plug that in, I'd have 400 take away 7, for sure positive. 100 take away 2, that's positive. A positive divided by a positive would be positive, so this part, or that interval there, is also going to be a part of my domain. So in this case, it would be from 2 to infinity. But as we mentioned right here, we can't equal 2, so I would make sure that I use a parenthesis to get rid of it. So the domain for this first f of g function would be those two intervals combined, where again I have to make sure I'm getting rid of the 2 because that was a problem in the g function. So let's go ahead and talk about maybe the other combination. What if I did g of f of x? That now, if I think of the order in which things are going, x gets plugged into g first. So if I look at what that, or sorry, into f first, misspoke. So since x is going into f first, I need to make sure that I'm fitting that domain. So that for sure is, I have to be greater than or potentially equal to that -4. So this is just like my bare minimum. Okay, that's satisfied my f of x function. Now I'm going to be plugging into the g. Well, with g I need to figure out what number would come out of f, or sorry, what number if I plugged it into f would come out as a 2, because that's going to be a problem in the g function. So what I do with that one is actually just take the f function, which was square root of x plus 4, and I just need to set it equal to that problem number, which was 2, and then solve, and then maybe on this interval here I have to get rid of maybe just a specific point or break it into a couple of other ones. So here to solve it, I would square both sides. So I get x plus 4 is now equal to 4, and if I subtract 4 from both sides, I think we'd see relatively quick that x would equal 0 in this scenario. 0 actually was on this interval that we had right here, this -4 to infinity. I need to actually get rid of 0 because that would have been the number that made the 2 happen that couldn't go into this g function. So I'm just going to break up the number line, -4 until I get to 0 where I don't include it. -4 was still allowed originally though, so it gets a bracket, and then unite that with the other side from 0 to infinity. So that would be my way of like just saying, okay, on this interval from -4 to infinity, if 0 was a problem, that's how I get rid of it. So -4 to 0, don't include it, and then 0 to infinity, also don't include it. That would be my domain for my g of f of x function. So as you can see, these are very complex and kind of have to think outside the box a little bit, but the more you practice it, the easier it may get. Hopefully these two, if you didn't understand, maybe press pause and rewind it, rewatch it, and just see if the explanation maybe makes sense a second time, or just come to class and ask me some questions and we can work through extra examples. I'm sure that this one example is not going to make it so you understand everything, but at least it hopefully gives you an idea of how to approach the type of problem. Well, I hope you guys are hanging in there on this video. I know it's starting to get a little bit long, but some of the content is pretty tough, so it requires a little bit more description. The last topic, this is the last topic, which is inverse functions, is hopefully a little bit more of a review so I can blaze through this a little faster. But by definition, a function f of x has an inverse that we denote with this f, what looks like a -1 power. So this is what we would call, or how we would say, this is f inverse. So just to get the terminology out in the open. So a function f of x has an inverse f inverse of x if and only if f of x is 1-to-1. So that's where the idea of doing the horizontal line test that I mentioned earlier could potentially be helpful. So if you have a graphing calculator and you weren't sure if the function was 1-to-1, you could get a graph on your screen and just do a quick little horizontal line test for yourself and verify whether it's 1-to-1 or not. If we compose the two functions inside of each other, so like doing f of f inverse of x, that should always turn into just plain x, because think of it as x would go into the inverse, and then that result would go into f, so it should turn right back into whatever I plugged in first, which in this case is the x. And it happens to work out that if I reverse the order, f inverse of f of x, that also needs to come out as x. So that would be a way that you could kind of test whether two functions were inverses of each other without actually having to find an inverse. Now, when it comes to finding an inverse, the first thing we need to do is, again, just verify that it is truly 1-to-1, so I can say at the very beginning whether it has an inverse function or not. Then I move on to the idea of replacing the function notation with a dependent variable. So in this case, more times than not, you're going to use the letter y. So if you had a function named f of x, you could replace it with y, for example. At that point, we then swap or interchange, whatever phrase you like better, whatever the independent and dependent variables are. So for most of the examples you guys have dealt with in the past, that's been the letters x and y. So you essentially just put y everywhere you see an x, and then put x everywhere you see a y. So once you have that all changed up, notice none of the numbers or powers would move. You're just replacing the letter that maybe those numbers or powers are on. And then at that point you do everything in your power to try and just isolate y. So you do the solve for y step, and if it truly was an inverse function, you would then replace that y value back with the function notation of inverse function, so f to the -1 of x as far as how it looks. Now as far as domain and range are concerned, remember if I'm swapping x and y, that the domain of our original function should actually equal the range of the inverse if I'm swapping them. Same thing I could say for the range. The range of f must be the same as the domain of the inverse function. Graphically, remember if you were to have, say, a function and its inverse graphed on the same plane, you would notice that it would actually be like a mirror image or a reflection across that y equals x line. And then as far as how some of the points relate to each other, if I knew that, say, 2, 3 was on one graph, the reversed order of that, so 3, 2 would have to be on the graph of the inverse. So now to come up with an example of this one, just to finish up this video, this one's just asking us to find the inverse function of this. So I first want to verify that it truly is 1-to-1. So if I were to think of the graph of this, the 0 of this would be whatever makes the inside 0. So I would add 9, divide by 2, so that would be 9 halves, so 4.5-ish. So if 4 is right here and 5 was right here, it'd start at 4.5, and then it would technically open to the right because there was no negative inside or outside to reflect that square root graph. There would be kind of a horizontal stretch if you wanted to think of this too as a horizontal stretch or a compression actually. But regardless, as far as the generic shape, it's this square root graph that does for sure pass the horizontal line test, so yes, this is 1-to-1. So since we know it's 1-to-1, I know it does have an inverse function. I just need to maybe take into account what my domain and range is for this. So my domain of this is going to be everything from that 9 halves, or 4.5, going to infinity. And then my range, as you can see visually, that's just going to be everything from 0 up. And so when it comes to finding the inverse function, I know that the domain of my inverse is actually going to be this 0 to infinity, so I can kind of take that into account before I even start the problem. Now to start actually finding the inverse, I go ahead and I've established the 1-to-1. Next thing I'll do is go ahead and replace the function notation with my dependent variable, which is going to be y in this case. And then now I'll swap the x and y in the next step, so that's going to give me x on the left now, and now y on the right inside with the other numbers that I had. So to start trying to get y by itself, I would first square both sides. So that would give me x squared being equal to 2y minus 9. Next step would be to add the 9 over. So if I add the 9 over, now I've got x squared plus 9 being equal to 2y. And then the last step would be to divide the 2 over, and that would give me an expression where I could say now y is equivalent to x squared plus 9 all over 2. And since I knew it was 1-to-1, I can actually get my final answer for this one would be the inverse function of x should be equivalent to x squared plus 9 all over 2. However, if we think of what that really is, that's a parabolic graph, right? X squared plus 9, then all cut in half. That's just been compressed a little bit and shifted up. So with this, I could now, because it's a parabola technically is not 1-to-1, I need to cut off half of it, so I would need to actually include my domain off to the side. So I could say it in this inequality notation, x just needs to be greater than or equal to 0. That way everything is in terms of variables. Or you could also, if you really wanted to, you could just have written the interval notation in that spot. But since I was using variables the whole time, it makes a little bit more sense to me to use the variable notation, which involved that inequality. But anyway, there's an example of finding an inverse. again, thank you guys for taking the time to watch this video. I know it was a little bit longer. Hopefully it's still helpful. Press pause, press rewind, do whatever you need to do with this video. Fast forward if you already know it, but you should have fast forwarded in order to make it here, so that doesn't really help. Anyway, as always, if you have questions, bring them to class. I'll do what I can to help you out. Again, thanks for watching the video, and I'll catch you next time.